Hi, my name is Taylor B, and I'm going to be introducing our final presentation for our report in ME440, or I'm sorry, ME404 finite element analysis. This is the analysis of a sprinkler system. My name is Taylor B, and my group teammates is Cole Tinsley and Joseph Wentz. So to quickly reintroduce this project, this is the analysis of a sprinkler system. The, I guess, inspiration for this really comes from the Pacific Palisades fire, where a homeowner was able to protect their house using a roof-mounted sprinkler system. So the idea here is that if we could come up with sprinkler systems and optimize the design, it'd be cool to be able to set these out on houses and protect them from wildfires and other fire-prone areas. The analysis of this project is primarily going to revolve around the force being applied onto the sprinkler. While we could do some CFD analysis with ANSYS, it's a fairly more advanced system and topic, and the modules that we've covered in this class thus far haven't really covered CFD. So in that case, we're just going to be limiting our analysis onto a structure, I guess more of a structure, a strain analysis.
Hi, I'm Joseph Wentz. I will be going over the preliminary calculations on the load on the deflector of the sprinkler. These calculations have stayed the same since the progress report. We are just using the fluid force equation to find the force and the Bernoulli's and continuity equation to find the velocity. We found the areas, the pressure, and the density online. We just plug those into the Bernoulli's and continuity and solve for velocity, and then solve for the force on the deflector. We found the velocity to be 52.6 inches per second, and we found the force to be 1.769 pounds. The force was converted to newtons for the Excel calculations, which I will also go over.
Hi, I'm Cole Tinsley, and I'll be going over some of the 3D design elements that went into our project, as well as the ANSYS simulations. This is the first deflector model that was probably visible in our midterm report as well. This was an initial approximation to get an idea of what the deflector that we were going to use would look like. We ended up going with something a little bit different, but this was for our initial approximations. It's not even to scale. This is just kind of the visualization. The idea is that it spins along the pin that would go in the center, and it's kind of an axial pin, so we could measure forces on that pin and the deflector. Bending is kind of centered around those flanges that come out from the circular area at the center, because as the fluid hits the plate, it'll disperse, putting force on those flanges, which would cause some bending. That was the initial 3D modeling idea. And this is what we ended up kind of moving towards, is these 3D iterations that took the whole sprinkler head into account. That first one on the left side was kind of made for simplicity in modeling it, because you have, we could just apply force at the top, bring it down, but then that wasn't really too functionally sound in terms of modeling the real situation. We ended up with more of this model on the right side being what we wanted to represent that force dispersion. So the force was dispersed across the top on that right picture, across the top of the deflector, and then the support is on the top side of the whole sprinkler head apparatus. You'll see more of that in the in the ANSYS simulations. But this was kind of the iteration that we went through, was a simpler one that we could model easily mathematically, and one that made a little more sense in terms of simulating it.
For modeling the sprinkler by hand and the Excel calculations, we use the direct formulation to analyze the sprinkler. We divided up the sprinkler so that there are 18 elements and 18 nodes, as shown in the picture on the right. We chose the force to be at node 1, applied directly to the deflector, and it is equal to 7.87 newtons which was converted from the pounds shown in the preliminary calculations into newtons for the sake of this analysis. We also chose the pin to be at node 18, where the sprinkler would be attached to the ceiling. The equations we use for the direct formulation have changed a little bit. The spring constant has not changed. It's equal to the Young's modulus times the cross-sectional area of the element divided by the length along the element. The deformation is now the matrix multiplication product of the inverse spring matrix times the force vector. The reaction forces were found using the K matrix times the deformation vector minus the force vector. In the post-processing phase, we have that stress is equal to the Young's modulus times the difference between the deformation at the second node minus the first node with respect to the element. All over the length across the element, the strain is equal to the stress over the Young's modulus, and the axial force is the stress times the cross-sectional area. Plugging that into Excel, we found that the highest stresses and strains were on elements 4, 5, 11, and 12. This is similar to what we saw in the ANSYS simulation, where the highest stresses were on 4 and 11. We didn't see that high of stresses on 5 and 12, though. We found that the highest axial forces were on elements 1, 2, and 18, which makes sense as this is where the force is applied and where the sprinkler is pinned. We also found that the highest deflection was on node 1, which is very similar to what we saw in the ANSYS simulation, where the highest deformations were on the teeth around the deflector. In Table 1, we see the results on each of the nodes. We have the deformation here in nanometers and the reaction forces in newtons. The deformation is, again, highest at node 1, and it goes to 0 at 18, where it is pinned. For Table 2, we have the element results. Again, we find that stress and strain are highest at 4, 5, 11, and 12, and axial force is highest at 1, 2, and 18.
The ANSYS simulation that you're seeing here is based on an equal dispersion of force across that deflector based on the dispersion of the liquid. It wouldn't be even in terms of force. It would be more concentrated in the center realistically, but we dispersed it evenly in the modeling because that was what we could do with our means. You see these kind of exaggerated bowing of the arms as well as a kind of deeper dip of the deflector. That's because ANSYS kind of exaggerates those things, and we used a greater force to get an idea of what deflection to expect under high strain. The force dispersion, like I said, similar to a fluid, and the circular object, well, the pin kind of that deflector is supposedly spinning on, and the deflector itself are where we're kind of calculating things. So this model did a good job of showing us kind of what to expect for deformation on the ANSYS simulation. Again, these flanges are deforming more highly because they're kind of thin and on the outside. We could probably fix that with ribs on the bottom or thicker deflector, or even just changing the shape a bit. This is a pretty simple model. Right. And these were shear stress analysis, which I thought was really interesting because it shows kind of the concentration and what to look out for when designing kind of anything really that's expected to undergo some forces. The shear peaks you can see on the top right. My camera's probably in the way. The shear peak on the top right was on the bottom side here, where that circular pin on which the deflector spins is connected to the bracket legs. And it's concentrated there because that's where the sharp edges of something coming down and the flanges which are held on that upward support. So you get that shear on these bottom sides. And on the bottom right side, you get that shear that's kind of a result of something that's being bent. And so you get that separation, and that ends up with a high concentration of shear there. Again, these are exaggerated shapes because, to visualize what's happening, but it's a pretty good approximation of what to look out for in kind of the design and the forces that are coming down and pulling it back up. Like I said, the very top of the sprinkler head is what's being supported flatly against probably the ceiling of whatever structure. So yeah, it's a pretty good visualization.
Thank you guys for watching. If you guys have any questions, be sure to let us know. Thank you. Take care.